Intelligent machine monitoring is back. As you may have noticed, we are here in a different setup, and here are my colleagues Tobias and Dominique. Actually, we are shooting here at our friends of Kötter Consulting Engineers. Thank you for this. The reason why we are here is that in this fourth feature, we want to talk about sensors. And not only about the measuring principle, but also where they're located on a machine. To give you a better impression of where the sensors are actually located, we have a test compressor here in this facility, and my colleague Tobias will give you now a short downturn on this machine that you know what we are talking about in detail.
Yes, Jos, thanks. Yeah, you see here our little reciprocating compressor. It's a double-acting, one throw, and we have the head end and crank end compression chamber, and it's a nice vertical machine. And it's important to show you very close where are the sensors, and let's start with that.
Hello, I'd like to present you the trigger sensor today. The trigger sensor is used to provide a phase reference and the speed information of the monitored machine. And I'm going to explain you the principle of this sensor first. Later on, I show you where it is mounted. So the trigger sensor is a Namur switch, and it's a proximity switch. So it works with the electromagnetic field in the sensor top. This electromagnetic field senses electromagnetic material in the sensor sensitivity range, passing by the sensor, and in the moment when the target or cam is passing by the sensor tip, the sensor will switch. This type of Namur trigger is a normally closed design, which means in a inactivated position or modus, when there's no target in front, the switch is closed and the signal is a high current. And in the moment where we the target passes the sensor, the switch is open and the current flow passing the sensors resistors is decreased. And now I'm going to show you where the sensor is located at the machine. Okay. The trigger sensor is pointing towards the flywheel of the compressor and is installed in a rigid bracket that is usually installed on the foundation of the compressor or on the housing of the motor. So the trigger sensor is installed in the bracket and is pointing to a target that we call trigger cam. The target is a ferromagnetic piece of metal mounted at the flywheel, on the flywheel with a metric screw. And as the flywheel is turning, this target passes the sensor tip once per revolution. That means we will get a phase reference to the position of the piston, which means we want to make sure we know when the piston reaches the top dead center position. Some important items for installation of the trigger sensor is we need to get the sensor adjusted in a way that the sensor tip has a distance to the target of approximately 1.8 up to 2 millimeters to ensure that the sensor is actually working in a secured and safe way, and we will not miss revolutions in between. Yes, and that is basically the main points to install a trigger sensor. Now we will continue with the next sensor. The next sensor is the pressure sensor. we're measuring the pressure inside the compression chamber as a dynamic measurement, which is a very fast changing signal, and so we need a fast responding sensor. So this sensor is a good example, and some special design sensor for a special purpose. In this case, with a special tip. The pressure sensors we are using have a very wide pressure range, so we can measure from absolute ambient temperature or absolute pressure up to a couple of bars, but the maximum we can measure is high pressure applications up to 6,000 bars. And the principle of the sensor I'm going to explain you here at the whiteboard. I prepared a little sketch. So we would have the process connection thread of the sensor where we screw the sensor inside to the machine. This is here. A typical connection thread would be a 1/2 inch G, which is a parallel thread. We use a GA type of thread. And you see here that we have an indication, a pathway for the medium, for the gas to enter the sensor. The gas will enter the sensor up to this certain point where we have a sealing and a synthetic oil, which is used in order to pass on the pressure, which is measured here at the diaphragm. So the medium is entering the sensor, passing on the pressure through the diaphragm seal to through the synthetic oil and the cooling ribs here to this sensor pressure sensing cell. The pressure sensing cell is inside the back part of the sensor here, and we will have an electronic amplifier after the right after the sensing cell that provides us a 4 to 20 milliamp output signal of this sensor, which is intrinsically safe application. And now I'm going to show you where the sensor is installed at the compressor. The pressure sensor needs a direct indication into the compression chamber, and we are going to measure the actual changing gas pressure inside the compression chamber on both sides, the head end side and the crank end side. A typical way to install is an indication bore that is inside the cylinder casing. The sensor is installed either, as you see it here on top, directly into the cylinder casing, or you could also install an isolation valve. If you want to install an isolation valve, we strongly recommend you to use ball valves instead of needle valves for the better signal, the better pressure signal. If you have a needle valve, the gas will not pass the way straight. It will be bent through the needle and the needle valve, and then we will have influence on the measured signal. This sensor here, as you see, could be equipped with a connector on top, or the latest types we use has an integral cable with 2-meter integral cable, and then we go to the extension cord. So this is because we want to avoid vibrations from the sensor on the connector. Usually, when the compressor is in operation, we have high level of vibration on the top of the cylinder, and that is the best method to have integral cable, and you can then attach the connectors to a rigid structure outside the compressor.
Yeah, let's talk about the acceleration sensor, one of the most important sensors we have in our machine diagnostic world, mounted to the machine with a little stud, screw it in and mounted to the sensor. And on the other hand, for sure, the electrical part, so it's a mill connector, very rugged and to have a good electrical connection. The sensor is looking like that, more or less. So we have the sensor housing, and in the middle we have the base element. And on this base element, when we talk this share, so-called share concept, then we have a seismic mass close to these connected with a little piezo element. Yeah, and when I look more close about that, then you have a look, that is my piezo element, and you see with all the electronic, and you have the plus and the minus, and you see when it's moving, when it's shaking, yeah, it's up and down, these piezo will be shifted and results in a special power. And that is more or less what we have here. Important is as well to see the frequency range. And when you talk about the frequency range, then we have the frequency, about the amplitude, and all the sensors have such a shape, and here with the reference point, and that is important to see that because we are measuring here in the range up to 10 kilohertz from 0.1 hertz, kilohertz, and measuring this range. And in look to the connection, so best is to connect it direct to the machine with this stud, but you can also glue it. Sometimes you have a test probe, and the connection here influenced resonance, so it moves. For example, when you're using a magnetic connection, for example, it moves further down, or when you have the test port or the test pin, then it's looking like that. So at the end, you increase your frequency range, what is not good, because we need a high frequency area to understand the failure modes. It's an Icp sensor. That means we have we supply current inside the sensor, and output is a voltage signal in the range of -10 to +10 volt. These sensors are offered in different sensitivities. It's from 10, 100, and 500 millivolt per G. And depends on the sensor position, we're using these different types of sensor measuring ranges. Yeah, now I want to show you direct on the machine the sensor positions. Yeah, here our machine, and in the bottom part, the crosshead slide with the sensor connected direct on the metal frame, and in here you see a variation of the sensor. It's a direct connected, but for sure, what I showed you before, you can use as well with connector when it's outside of the machine. That is crosshead vibration signal. On the other hand, we're looking for the cylinder vibration, and the acceleration measured there. We are close to the valves on the cylinder head to see really the valve impacts coming up and down. Yeah, here's a nice example to use two components epoxy adhesive and to have a good connection to this housing of the cylinder. And now I show you the next sensor. And now I'm talking about eddy current proximity probe. We use it for the displacement measurement of the DC and AC value for the piston rod position. And it's an eddy current. That means we have a coil inside the sensor which influenced a magnetic field to the metal target, our piston rod, and depends on the distance between the sensor and the target material. We got a different initiated current value, what is sensing by the coil back and given a result. The sensor always works together with a converter. I'm not showing here. You see here the sensor, which is inside the sensor in the proximity head. We have the coil I showed you before, and this coil generated the magnetic field depending on the material, on the distance to the material. We're receiving back a definite current, which at the end, the high frequency signal given distance value with a converter to our system or to the measuring system. I show you here how it works. So we got in the voltage, and depends on the voltage and the sensitivity of the sensor, we got the results of the distance. So that means lower distance is in the area of 2 volt, minus 2 volt, and higher distance is in the area of 18 volt or up to 18 volt. Important is that we always have a linear area, yeah, and up a certain point it becomes unlinear. So we have to focus and we have to locate the sensor always that we are in the middle of the linear area. Yeah, so when we start to measure, or when we mount the sensor to the target, we start with a fixed distance, which is in the middle of the linear area. For example, here 1 volt or 1 millimeter, and we call these the zeroing of the sensor. One other issue is that we have a so-called air gap. So the sensor is not able to measure close to the target. So it starts measuring in the area of 0.1 millimeter. Now I show you this sensor located on the machine. Have a close look to the machine. The measuring position of the eddy current proximity measurement is here direct on the piston rod. The position is close to the so-called stuffing box and the other side of the motion area of the machine. The sensor is located close to the machine here in X and Y. When we have a horizontal machine, we only have it on the top solution, and the sensor is adjusted on a fixed distance, and so at the end the signal is giving the dynamic and the static and the dynamic part.
Tobias, Dominique, thank you very much. That was quite a piece. I think you have learned a lot about sensors, their measuring principles, and their location on the machine. Also, thanks again to Kotter Consulting Engineers for having us here. And as always, like, share, subscribe if you like what you have seen, and leave your comments below. See you next time here at Intelligent Machine Monitoring.